changes in today's schedule. The order of the talks is the same, but just that the first talk by Boris Kayser will be from 9 to 10:30 rather than 10:15. And we'll break for coffee at 10:30. From 11 to 12:30, we have Andre Di Govia. And then at 12:30, we'll have a Skype talk by Nama Mondal till 1:15. And we break for lunch at 1:15. Get back at 2:15, not 2:30, so that we have enough time for the neutrinoless double beta decay talk as well. Thank you.
So, good morning, and we start with the first talk today, Tensions with the Three-Neutrino Paradigm by Boris Kayser.
I'm going to be talking about the possibility that there are more than 3 neutrinos. Experimental hints that there may be more than 3 come from experiments on neutrino oscillation. So to make sure that everybody can follow, I'm going to begin with a general review of the basics of neutrino oscillation. First of all, what is neutrino oscillation? There are 3 flavors, as we all know, of charged leptons: the electron, the muon, and the tau. Correspondingly, there are 3 known flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. We define these neutrinos of specific flavor through W boson decays. When a W decays leptonically, it can create either an electron, a muon, or a tau, and an accompanying neutrino. We define the electron neutrino as the neutrino state which is produced when the charged lepton is an electron. The muon neutrino is the state which is produced together with a muon, and similarly for the tau neutrino. And as far as we know, when interacting, a neutrino of given flavor creating the charged lepton creates only the charged lepton of the same flavor as the neutrino. So a new E creates only electrons, a new mu only a muon, a new tau only a tau. That means that if a neutrino is born this way in W decay together with a muon, so that at birth it is by definition a muon neutrino, and it travels only a short distance during which it does not have time to evolve into something different, and then it interacts in a detector and makes a charged lepton, this charged lepton is never going to be an electron. It's going to be a muon. It's going to be of the same flavor as the neutrino. And that observation is a big part of what led to a Nobel Prize for these 3 people. On the other hand, if neutrinos have non-zero masses and leptons mix, then you can have a scenario like this one, in which a neutrino is produced in pi decay through a virtual W. The pi almost always decays to a muon, so at birth this would be a muon neutrino. And then if you send it on a long journey during which it does have time to evolve into something different, if it then in a detector makes a charged lepton, that charged lepton we observe is not always of the same flavor as this neutrino was born as. It can be, for example, an electron. And since, as far as we know, it's only an electron neutrino that makes an electron, that means that during this journey, the neutrino has changed from what it was at birth, a muon neutrino, to an electron neutrino, or at least into a state that has an electron neutrino component. This is the phenomenon which is referred to as flavor change. It's usually depicted this way. And notice that the defining characteristic of flavor change is that the charged lepton that the neutrino makes in the detector is a different charged lepton than the one with which the neutrino was born. The last 15 years have brought us very convincing evidence that such flavor changes actually occur in nature, and the next speaker is going to be talking about some of that evidence. Neutrino flavor change, as we'll see, requires non-zero neutrino masses. This means that there must be some spectrum of neutrinos of definite mass, neutrino mass eigenstates, nu1, nu2, nu3, and we'd like to know what that spectrum is. Flavor changes we'll also see requires leptonic mixing. That is, the neutrinos that I started out talking about are not these mass eigenstates. Rather, each neutrino of definite flavor is a quantum superposition of the mass eigenstates, like that. I'm going to use a Greek subscript like alpha to mean a neutrino of definite flavor, nu e, nu mu, or nu tau, and a Latin subscript like I to mean a neutrino of definite mass. The coefficients in this relationship are elements of a matrix which is referred to as the leptonic mixing matrix, or sometimes as the Ponte-Corvo-Maki-Nakagawa-Sakata matrix, to honor 4 pioneers. It is the leptonic analog of the CKM matrix that Marina was talking about yesterday. Since, as you see, this is a transformation from one quantum basis into another, you expect it, like all such transformation matrices, to be unitary. Another way of stating what this relation says is to say that when a W decays into a charged lepton of flavor alpha, I see I run over the bottom of the screen. I'm tempted to make a joke by moving my laptop slightly, but I don't think that would fix it. I'm going to use the notation script L to mean a charged lepton, generically. And charged lepton sub alpha is the one of flavor alpha. L sub E just means the electron. L sub mu just means the muon. L sub tau is the tau. Suppose the W decays into a charged lepton of flavor alpha, and I'm going to take it to be an anti-charged lepton in particular because should lepton number be conserved, then since this is not a lepton, if you want to make a neutrino, you have to make an anti-lepton over there. So I want to make a neutrino, so I'm going to take this to be an anti-lepton. What this says is that when you make an anti-lepton of flavor alpha, so that the accompanying neutrino state is nu alpha, the amplitude for this nu alpha to be in particular the mass eigenstate nu I is just the coefficient of nu I in this expansion, that is u star alpha I. And then by simple quantum field theory, when this nu I is incoming and makes a charged lepton of flavor beta, the amplitude for that charged lepton to in particular have the flavor beta is the beta I element of the same matrix without a star. I'm going to use these two relations very shortly. So here's a theorist's eye view of an oscillation experiment, and we'll see shortly why it's called oscillation. Here's a neutrino source which through W exchange creates an anti-charged lepton of flavor alpha, an anti-muon for example, and a neutrino which then goes down some long beamline. After traveling a long distance by another W exchange, it interacts with some target in a detector and it makes a charged lepton of flavor beta, for example a tau. This is what we would call a nu alpha to nu beta flavor change, or oscillation. On the other hand, if nu alpha is a superposition of mass eigenstates, then because you're not going to know which mass eigenstate actually went down the beamline in each event, the amplitude for nu alpha to oscillate into nu beta is the coherent sum of the contributions of the different mass eigenstates. This just repeats that statement, and now the contribution of mass eigenstate nu I consists of several factors. First of all, there is the amplitude that the neutrino born in association with L alpha bar is in particular the neutrino mass eigenstate nu I. As I just told you a couple of slides back, that amplitude is u star alpha I. Then there is the amplitude that when this nu I interacts in the detector and makes a charged lepton, that charged lepton has in particular the flavor beta. That, as I also mentioned, is u beta I. Finally, there is the amplitude that this neutrino gets from here to there. That amplitude is just e to the minus I times the rest energy of the neutrino times the proper time that elapses in its rest frame during the journey. This is just a rest frame version of the familiar plane wave factor e to the IPX minus ET. Now one can show that at least to a good approximation, you can re-express this propagator in terms of lab frame variables in this way, where L is the lab frame distance that the neutrino travels, and E is its lab frame energy. And so putting this all together, you see that the amplitude is just this simple sum of these three factors summed over all the neutrino mass eigenstates, and then the probability that a neutrino born as a new alpha later interacts as a neutrino of flavor beta after having traveled the distance L with energy E is just the square of this expression. Taking that absolute square and making some sneaky use of the unitarity of this matrix, we find that the probability for new alpha to oscillate into new beta is given by this formula, where delta m squared ij is just the difference between the squared masses of mass eigenstates nu I and nu j. Now the most important thing about this result is if all the neutrinos were massless, so that in particular all the mass splittings would be 0, then you see everything drops out except the initial delta alpha beta. In other words, there is no change of flavor from one flavor to a different one possible. So the observation that neutrinos can, in fact, change from one flavor alpha to a different flavor beta requires non-zero neutrino masses. And that's how non-zero neutrino masses were discovered. They were discovered through the observation that neutrinos can oscillate from one flavor to a different one. Now, I've been talking so far about the oscillation of neutrinos, not antineutrinos. Let's talk for a moment about the difference between the two. The neutrinos we encounter in the laboratory are in practice always of left-handed helicity. The antineutrinos we encounter are always of right-handed helicity. As a result, the symmetry operation that takes you from this oscillation among the antineutrinos we encounter, right-handed ones, into this oscillation among the neutrinos we encounter, left-handed ones, is not C, but CP. C, charge conjugation, will turn the antineutrino into a neutrino, but P is also required to reverse its helicity. Similarly, the effect of CPT on nu alpha bar going to nu beta bar is the same as CP, but with an additional operation of T, which reverses the initial and the final state. It reverses the arrow of time. As a result, if CPT invariance holds, which I absolutely believe it does because it's a fundamental property of field theory, and if that's wrong, I don't know what to do. If it holds, then what you see is that the probability for nu alpha bar going to nu beta bar, this reaction, should be the same as the probability for its CPT mirror image, that reaction. Now going back to the formula for neutrino oscillation that we just had, here is nu alpha going to nu beta. Nu beta going to nu alpha, you see, would just interchange alpha and beta here, which interchanges u with u star. So, if CPT invariance holds, then the probability for nu alpha bar going to nu beta bar is the same as the probability for the corresponding oscillation of neutrinos with the same initial state, with the same final state, but with the mixing matrix replaced by its complex conjugate. So summarizing that, here now are the probabilities for both neutrino and the antineutrino oscillation. It's the same as the neutrino formula, but if U goes to U star, when we go to antineutrinos, this imaginary part flips, so I've taken that into account by putting a minus sign there. Now, as we already discussed, these two reactions are CP mirror images of each other. What you see is that if U is complex, so that in general it will have a non-zero imaginary part here, the probabilities for corresponding neutrino and antineutrino oscillations will differ because of this change in sign. And any such difference would be a violation of CP. Now in the leptonic sector, the only CP violations we've seen so far in the laboratory have been among the quarks, in KDK, in BDK, experiments like that. This would be leptonic CP violation. Now there are some important special cases one of them particularly important to what I'm going to be talking about shortly. Suppose you're doing an experiment in which the neutrino spectrum, though we know it has more than 2 levels in fact, is effectively 2 levels. This can be the situation if there's actually a bunch of neutrinos here and there's another bunch of neutrinos there, but the L over E of your experiment is sufficiently small that you can only see the largest among all the delta m squareds ij. The smaller delta m squared ij's times your L over E make what's in this parenthesis so small compared to 1 that these sign factors are effectively 0. So in your experiment, there may be many neutrinos here and there may be many neutrinos there, but you can't see the splitting between them. You can see only the big splitting between these 2 bunches. So for you, it's effectively a 2-level system. When that's the case, that complicated formula becomes much, much simpler. The probability for mu alpha to oscillate into a flavor beta different from alpha is given by a formula like this. It involves only one wiggly factor involving the 1 delta m squared that you're sensitive to, and then there's some coefficient out front which had better not be bigger than 1, or the probability would be bigger than 1. And this is conventionally written as sine squared of twice some angle. I'll call it theta alpha beta. Similarly, the probability for mu alpha to remain with its initial flavor, in other words, not to go into anything else, is given by this formula, the same wiggly factor, and some other angle, sine squared 2 alpha, theta alpha alpha. Now, a couple of points. This experiment, if you were to look for this, is one in which you're looking for the appearance of a new flavor beta that typically will not be present in the beam to begin with. So this is called an appearance experiment. Here you look for the new alpha to remain a new alpha, or equivalently, you look for the new alpha to disappear through oscillation into other flavors. You do the experiment by knowing how many new alphas are in your beam to begin with and looking for some of those new alphas to disappear. So this is called a disappearance experiment. Another point, Kobayashi and Maskawa showed that a phase in the quark mixing matrix, the quark mixing matrix now, can lead to CP violation, but only if there are at least 3 families of quarks. The neutrino oscillation analog of that statement is that neutrino oscillation can violate CP, but only if there are at least 3 neutrino mass eigenstates and their masses are all different. So that when you go to this effectively 2-level system, so it looks to you like there are only 2 different masses, there's not enough physics to violate CP, and as a result, in this situation, the probability of neutrino oscillation and the probability of antineutrino oscillation, both in flavor change and in flavor non-change, are the same. No CP violation. Final point, it is important to realize that this parameter and that parameter are not the same parameter. You frequently will see plots, and I'm going to be showing you a bunch of them, in which people talk about sine squared 2 theta without telling you which theta they're talking about. What they mean is they're talking about the theta that they're talking about. And it's usually different than what the other guys are talking about. This is the probability that the neutrino does not change its flavor, that it does not disappear. That, of course, is equal to 1 minus the probability that it does disappear. So this second term is the probability that it does disappear, without regard to which flavor beta it's disappearing into. This is the probability that it disappears in particular to the flavor beta. So this disappearance probability has to be equal to the sum of these appearance probabilities for all the betas not equal to alpha. Since these 2 wiggly factors are the same, that means that sine squared 2 theta alpha alpha is the sum over all beta different from alpha of sine squared 2 theta alpha beta. The final special case, a very, very famous one, is when there are really only 2 flavors and only 2 mass eigenstates. So there's only 1 delta m squared. There's really only one mass at the bottom, 1 mass at the top. The mixing matrix becomes a 2 by 2 rotation matrix depending on a rotation angle called the mixing angle. And now the probability for mu alpha to oscillate into the only other flavor there is, beta different from alpha, is given by this expression, and the probability for it not to go anywhere is 1 minus that expression. And now these two thetas are the same theta, because there's only one place that nu alpha can go. There's only one other flavor, so there's no sum to be done. I've been talking so far about neutrino oscillation in vacuum. However, if you build a beam of neutrinos, let's say at Fermilab, the place where I work, and you send that beam to a detector somewhere deep underground in India, then because of the curvature of the Earth's surface, the neutrinos are traveling through Earth matter. Their interaction with the electrons in the Earth matter is going to modify the way in which flavor changes. The nu E component of the beam can exchange a W with an electron in the Earth if it's a neutrino through this diagram, and if it's an antineutrino through that diagram. These diagrams have small amplitudes, of course. These are weak interactions, but the coherent forward scattering via either this diagram if it's a neutrino beam or that one if it's an antineutrino beam leads to an extra interaction potential energy, which the standard model tells us is of this amount, where GF is the Fermi constant and NE is the number of electrons per unit volume. This amount if it's a neutrino beam, and the opposite amount if it's an antineutrino beam. This raises the effective mass of electron neutrinos in matter, and this lowers the effective mass of electron antineutrinos in matter. And the reason that it's only a nu E that does this is that, remember, as far as we know, the only neutrino that can do this and make an electron is a nu E. The fractional importance of matter effects on an oscillation involving a vacuum splitting delta M squared can be measured by this parameter I call X, which is the extra interaction energy I just spoke about, divided by delta M squared over 2E or over 4E, something like this. Notice several things. First of all, the fractional importance of the matter effect grows with the energy of the neutrino beam. Secondly, it is sensitive to the sign of the mass squared splitting between the two mass eigenstates. That is to say, if you have two mass eigenstates, and you know, for example, that one of them couples a lot to electrons, and the other one couples only rarely to electrons, the matter effect can tell you which of those two is the heavier and which is the lighter. Finally, because of this reversal in this interaction energy when you go from neutrino to antineutrino, the matter effect is going to reverse when you change your neutrino beam into an antineutrino beam. That means that when you do a neutrino oscillation experiment with neutrinos and then you repeat the experiment with antineutrinos, you expect to see a difference even if there is no CP violation because of this matter effect. It's a kind of a fake CP violation caused by the fact that the Earth is not CP symmetric. It contains electrons but not positrons. One final obvious point. Neutrino flavor change is always called oscillation. The reason it's called oscillation is that the probability for it oscillates as a function of distance divided by energy. Okay, now with that preamble, I get to talk about the evidence that there's more than 3 neutrinos. First of all, what is the standard 3 neutrino picture that the data are suggesting may be incomplete? That standard 3 neutrino picture says that there are just 3 mass eigenstates, nu1, 2, and 3. 2 of them are separated by this very small delta M squared, and the third is separated from this closely spaced pair by this roughly 30-fold larger delta M squared. We don't know whether the closely spaced pair is at the bottom of the spectrum or at the top. If it's at the bottom, then this spectrum resembles qualitatively the charged lepton spectrum, the up quark spectrum, and the down quark spectrum, and for that reason it would be called normal. It just means like the others. If, on the other hand, the closely spaced pairs at the top, the spectrum would be called inverted. And as I say, we don't know yet which it is, but we know the sizes of these splittings. In the standard three-neutrino picture, it is assumed that the interactions of neutrinos are those of the standard model, modified to incorporate leptonic mixing, the presence of that mixing matrix. That means, as we said, that a neutrino of flavor alpha couples to a W and only the charged lepton of the same flavor alpha, but the neutrino of flavor alpha is a quantum superposition of mass eigenstates. Turning to the neutral weak boson, the Z boson, according to the standard model, the Z boson couples universally and diagonally to the neutrinos, whether you're in mass eigenstate basis or in flavor basis. So the neutrino, the Z boson doesn't care what flavor this neutrino is, so long as it's a new E or a new mu or a new tau. And it's not going to change it into a different flavor. When you have a process like this, in which the lepton does not change its charge, it is referred to as a neutral current process. And because the Z boson doesn't care what the flavor of the neutrino is, oscillation among mu E, mu mu, and mu tau will not change the neutral current event rate. If the mixing matrix, as it is in the three-neutrino picture, is 3 by 3 and unitary, it can be written as a product of 4 factors like this. One of those factors does not affect oscillation, although it affects neutrino double beta decay, which one of the later speakers will be talking about. The other factors involve the cosine and the sine of various mixing angles, theta 2, 3, theta 1, 3, theta 1, 2. And we now know what all of those 3 mixing angles are. They're big. The best fit for theta 2, 3 is somewhere around maximal mixing, that is to say 45 degrees. Theta 1, 2 is also pretty big, although not maximal. Theta 1, 3 is not so big, but it's not so small either. If there is this phase factor making the mixing matrix complex in a way that's going to lead to that imaginary part in the oscillation formula that I quoted for you, then this phase factor is going to lead to a CP violating difference between the probabilities for corresponding neutrino and antineutrino oscillations, the leptonic CP violation. Notice, however, that this phase factor, which could produce CP violation, occurs only multiplied by the sine of theta 1, 3. For that reason, there was for a long time a worry before theta 1, 3, the last of these angles to be actually determined, might be very small or 0, in which case there wouldn't be any visible CP violation in neutrino oscillation. And if theta 1, 3 is 0, there isn't any CP violation, period. It's not that you can't see it, it's that it's not there. But now we know that theta 1, 3 is not anything like 0. So there is no more worry, and now people are very excited about doing experiments that would look for this CP violation. The range varies. The 1 sigma here is something like 1.5 degrees. This is the 90% confidence level range, and this is actually, I think, more like 3 sigma. In any case, I mean, the main point is that we know where these angles are. Now, that simple picture very successfully describes many results on oscillation, and Andre de Gavea is going to be talking about that. But that picture does not successfully describe everything that we observe. So there are hints that there may be more than the 3 mass eigenstates in the 3-neutrino picture. and what is related that there may be sterile neutrinos. A sterile neutrino is one that does not couple to the standard model W or to the standard model Z. Now, there aren't all that many really compelling models that involve sterile neutrinos, but typically one imagines that if a neutrino doesn't couple to the W or the Z bosons of the standard model, it nevertheless does couple to something which we haven't discovered experimentally yet. So if it should be established that there are sterile neutrinos, that would motivate searches for the rest of the new physics for whatever it is these sterile neutrinos actually couple to, searches that could be carried out at the LHC or elsewhere. Now let's talk about the experimental hints that there might be sterile neutrinos. The first hint came from an experiment called LSND. LSND reported a rapid new mu bar to new E bar appearance oscillation at an L over E of order 1. They reported this oscillation probability to be about 0.25%. Now, if you see the oscillation, then evidently what's inside this bracket is not very, very, very tiny, which means that if this L over E is of order 1, delta M squared should also be, in these units, approximately of order 1, which is to say you require a splitting of order 1 electron volt squared. Now that is bigger than the two splittings I talked about before in the three-neutrino picture. And if what LSND is seeing is really oscillation at this short baseline, as it's called, pointing to a big delta M squared, then there must be at least 4 mass eigenstates. 1, 2, 3. This can be one of those, and then there's a fourth one. Now, if we have 4 mass eigenstates, then we can form 4 orthogonal linear combinations of those mass eigenstates that will be neutrinos of definite flavor. 3 of them are nu E, nu mu, and nu tau, and then there's one more. We know from the width, the rate at which the Z decays into neutrino pairs, measured at LEP, that the Z couples only to 3 different flavors. It's something like 2.98 plus or minus 0.02, which sounds suspiciously like 3. Therefore, if there are 4 flavors, then one of them does not couple to the Z. And the structure of the standard model is such that if it doesn't couple to the Z, then it doesn't couple to the W either. And that's what we call a sterile neutrino. So if the LSND effect is a genuine oscillation pointing to a big delta M squared, then there is at least one sterile neutrino. Notice, however, that what LSND points to is a big delta M squared, and you will see that as we go through the various hints, that's what they're all pointing to, a big delta M squared. They're not pointing to a specifically sterile property of what is going on. They're pointing to a big delta M squared, but that has the consequence that there's more than 3 mass eigenstates, and that in turn has the consequence, because of the Z width, that there's sterile neutrinos. Here, making the two-level approximation, is the region of delta M squared and sine squared 2 theta, the theta that matters to this plot, favored by LSND. It's indicated in blue here. There is another similar experiment to LSND called Carmen, which excluded part of this region. It excludes what's to the right of this brown curve, but that still leaves a good bit of the LSND region. And then there is a reactor experiment called Bouget, which, assuming CPT invariance, excludes what's to the right of the green line. But there's still a region of LSND space that's allowed. The Minibeam experiment was launched at Fermilab to confirm or to refute LSND. Minibeam has an L and an E that are both much bigger than they are in Ellis and D. The systematic effects in Minibeam are different than those of Ellis and D. But the ratio L to E, which is what counts for oscillation, is comparable to its Ellis and D value. So this is a good test. Minibeam has reported both the process reported by LS&D and its neutrino analog. And here are its latest results. These are the neutrino results. These are the anti-neutrino results. The rate for nu E up here and for nu E bar, candidates down there, is the black points, of course. In colors are the various known backgrounds. And you see that both in the neutrino case and in the anti-neutrino case, there is an excess of nu E or nu E bar candidate events over known backgrounds. And if you put these two things together, the excess is something like 240 plus or minus 60 events. Notice that there's a pretty big rise at low energies, and there has been some worry and continues to be some worry that whatever is going on at the higher energies, what is going on in the lowest energy bins is something other than oscillation. I will come back to that. But this is what they say. And now, inside these curves, which have various confidence levels, are the regions that are allowed by both the neutrino and the anti-neutrino Minibeam data, including all of the data, analyzing it in terms of oscillation, assuming it's oscillation that describes everything, including down to the lowest energies. All right, so inside this curve, there is an allowed region for Minibeam, and also the blue is again the LS&D. It's allowed by LS&D also. Bourget would cut this off at about here, but there's a region here which is allowed by both Minibeam and LS&D and Carmen. There is another hint which comes from a rather different source. Nuclear power plants produce many nu E bars. And people think they know how to calculate the flux of nu E bars as a function of the power output from the reactor with pretty good precision. In the last 2 years, the prediction of this nu E bar flux has increased by about 3%. That may not sound like a lot, but it has a big impact. The typical energy of the neutrinos from a power plant is around 3 MeV. With this increased prediction of the unoscillated nu E bar flux, measurements of that flux at detectors that are from 10 to 100 meters from various reactors now show that about 6% of the nu E bar flux is missing, possibly having disappeared through oscillation into other flavors. So here are the data. This is the observed event rate as divided by the experimentally predicted rate as a function of the distance to a particular detector. These are the various detector data points. You notice that the error bars are quite big, but these points do systematically appear to be below 1.
Systematic error is 3%.
I'm sorry?
Systematic error is 3%.
I don't hear your last 3 words.
I'm sorry, the systematic error is 3%. 3%.
Is that a statement or you? That's an opinion, I believe.
Look there. I'm sorry.
Still, I'm not defending these hints. I'm just reporting them to you. I'll tell you my opinion later. Later. Okay. Now, if you assume just 3 neutrinos, then you need a relatively large L over E. And those neutrinos have the delta M squareds that we have in the standard picture. Then you need a relatively large L over E before this curve of oscillation probability departs from unity. You have to get way out here. And here's what it is for an outdated value of theta 1,3, we now know this is something more like 0.09, but never mind. The point is that this curve doesn't depart from unity until you get way out here. On the other hand, if you add a big delta m squared, large compared to 1 electron volt squared, then already there has been an oscillation when you get to the closest in detector, and you have no trouble fitting these points. So again, what this is it's a hint, only a hint, for a big delta m squared. Finally, there's a hint from what is observed when a very intense radioactive source, this one or that one, is put into a solar neutrino detector to test that detector. These are sources of electron neutrinos, the same as the particles that come from the sun. And when they're put into certain detectors, it is found that the rate of mu e's that is detected in these detectors is lower than what one would have expected these detectors to produce. So some people are interpreting that as a hint that these electron neutrinos from these sources are already oscillating when they go a few meters, the size of one of these solar detectors. That's a short baseline oscillation, and again points to a big delta m squared. Now here I have a problem with this. The purpose of putting these sources into the detectors was to test the detectors. They were put into the detectors, and the detectors detected less flux than one thought the sources were producing. You can blame that on neutrino oscillation if you want, but I can also blame it on the detector. And so this is a hint, just a hint.
You could blame it on the source also. How do you know what the source is?
I don't.
You don't know the cross-section,
But if these sources were used to test detectors, I'm willing to suppose that somebody thought they knew what the source intensity was. That's for sure. That's always the case. Now, not every short baseline experiment sees a positive signal. There are negative short baseline experiments too.
Can they not make the baseline bigger and see oscillation back into electron?
Say again?
Can they not make the baseline bigger and see oscillation back into electron?
Not if you're inside you talking about these source experiments? No, you can't. I mean, you have the baseline. It's inside the detector. The baseline is the size of the detector, no more. Now, here is one negative experiment. Not the only one. This is a rather stringent one. This experiment looks for the disappearance of muon neutrinos, more specifically muon antineutrinos. However, if you assume CPT invariance, which I do, then the probability that a neutrino, an antineutrino of a certain flavor disappears into all the other flavors is the same as for the corresponding neutrino disappearance. So I'm not going to distinguish between neutrino and antineutrino disappearance. The most recent and most stringent limit on mu bar disappearance comes from a joint analysis of two experiments, Cyboon and Minibeam, that are in the same beamline at Fermilab. So the Cyboon detector, which is out here at about, let's say, 75 meters from the middle of the pion decay region, which is making the neutrinos, this serves as a near detector. And then Minibeam, which is farther, serves as a far detector. And you compare the mu bar signals in the two detectors to see if anything that was there disappeared by the time it went there. The results are compatible with no disappearance. And here is what they exclude. They exclude everything to the right of this curve. This brings me to the question of the mass spectrum and the connection between appearance on the one hand and disappearance on the other hand. In these short baseline experiments, one cannot see the splittings between the standard three neutrinos of the three neutrino picture, nu1, 2, and 3. So you can take these three neutrinos to be degenerate. And then to introduce a big delta M squared, which your data are pointing to, you add either 1 or 2 or 3 additional mass eigenstates. So these are called the 3+1, 3+2, and 3+3 spectra. Now remember, we said that when you have an effectively two-level spectrum, which you do here, you can't have CP violation. So this is going to predict the same behavior for neutrinos and antineutrinos. Here you can have CP violation. If, for example, you have a 3+3 spectrum, you have 6 mass eigenstates. You can form out of these 6 mass eigenstates 6 definite flavors. 3 of them are nu, mu, and tau, and then there are 3 sterile flavors. The mixing matrix connects this basis to that basis, so it is 6 by 6. Very complicated. It is presumably unitary, since it's a change of basis, but if you try to do an analysis in which you think that the only thing that's there is this 3 by 3 subpart of the actual matrix, this 3 by 3 part is not going to be unitary. Now, strictly as a result of the CPT invariance constraint that these two probabilities have to be equal, it follows rather quickly that the probability for nu Ebar to disappear, which is perhaps 6%, according to the reactor experiments, has to be at least as big as the probability for the oscillation reported by LSND as 1/4%. Well, that is very easily satisfied. This is not a very stringent connection. On the other hand, before going on, the obvious point, it would be very interesting to have a non-reactor probe of nu Ebar disappearance, and I will mention ideas for doing that, to test whether the reactor flux is really disappearing. Now, you can do better than this if you make assumptions about what the spectrum looks like. Assuming a 3+1 spectrum, the probability for flavor change, the probability for the corresponding 2 disappearances are given by these formulas. You have 4 neutrino mass eigenstates now, nu 1, 2, 3, and 1 more. So the matrix, the mixing matrix, is 4 by 4, and here are some of its elements. Delta M squared 4, 1 is the big splitting, that's the only splitting that these short baseline experiments can see, between the extra mass eigenstate that you've introduced, nu 4, and the degenerate nu 1, 2, and 3. Since this is a two-level system, the same expressions hold for antineutrino oscillation because there's no CP violation. Now, what LSND says is that this oscillation probability, for antineutrinos to be sure, is non-zero, but it's small. It's around 1/4%. And Bouguer does not allow you to make this small by making this delta M squared small. So these coefficients have to be small. And if these coefficients are small, that means that what's in parenthesis here is 1, and what's in parenthesis there is 1. And now if I do an experiment in which my L over E is at least big enough that I have several oscillations already in here, and my uncertainty in the energy is big enough that I'm averaging over these oscillations, you can replace all of these sine squareds by 1/2. And if you do that, the product of the 2 disappearance probabilities has to be approximately twice the probability of the appearance. And I put bars over here because this is the oscillation that LSND reports. This is the oscillation that the reactors report. And this is something we don't know much about yet, but there is this limit that I just reported. LSND tells you that the right-hand side of this equation is about 0.005, 0.5%. The reactor experiments tell you that this is about 0.06, 6%. So you see, this relation will be satisfied if the nu mu bar disappearance probability is about 1/10. Now let me go back a few slides. Let me take a guess. Here was the limit from the Minibeam-Seiboon experiment. We need something like here. And you see it's already looking a little dicey. Now that's 3 plus 1. The 3 plus 2 spectrum is, of course, more complicated, and the oscillation probabilities are correspondingly more involved. However, if the extra neutrino states that you add, nu4 and nu5, are largely sterile, which is to say, again, that these parameters are small, then you get the same kind of relationship that I just quoted, except at this time, the left-hand side is at least as large as the right-hand side, and it's allowed to be bigger. So again, you want a pretty big oscillation probability when you're doing a disappearance experiment. The 3 plus 3 spectrum is more complicated still, and I don't have a relationship like this to quote you, but the upshot of these considerations is that if nu bar to nu bar is really of order 1%, as LS&D is suggesting, then the corresponding two disappearance probabilities should both be of the order of the square root of 0.01, which is to say 10%. And that's a target that people are looking for. So far I've been talking about terrestrial hints that there might be sterile neutrinos. There's also a hint from cosmology. Big Bang nucleosynthesis and the cosmic microwave background anisotropies count the effective number of relativistic degrees of freedom and effective at early times in the universe. Now, if there are light sterile neutrinos with masses like 1 electron volt, and if these sterile neutrinos are mixed with the active ones to the degree that's required by the terrestrial anomalies, then these sterile flavors would very likely have thermalized in the early universe. That is to say, the number of sterile neutrinos per unit volume would have been as given to you by the conditions of statistical equilibrium. The same as holds for the active neutrinos. Now, each active neutrino contributes 1 to this N effective. And if you have a thermal population of sterile neutrinos, each sterile flavor contributes 1 to N effective also. What does the evidence suggest? Here is the evidence from Big Bang nucleosynthesis, and what I would like you to notice is that these numbers have a tendency to look like more than 3. More than the 3 that you would expect from just nu e, nu mu, and nu tau. Here is the evidence from the cosmic microwave background, and notice that the number of effective degrees of freedom looks a lot more like 4 than it looks like 3. In fact, it's even compatible with bigger than 4, like 5 and 6. Now, you shouldn't be impressed by how long this table is. Different lines in this table use the same data in many cases, just different combinations and used in different ways. But what is interesting is this does look more like something bigger than 3 than like 3. The early universe tells us something else. Large-scale structure in the universe and the CMB give us information about the sum of the masses of the different mass eigenstates. And depending on what data you use and what assumptions you make, that sum is constrained to be less than some small fraction of a volt and something like 1 volt. Now, if the tighter of these constraints is really true, then there is some tension with the terrestrial experiments that call for delta m squared bigger than 1 electron volt squared, which of course is impossible unless at least 1 neutrino weighs at least 1 volt, contradicting this. On the other hand, cosmologists tell us that there are parameter degeneracies in cosmology. In order to say something about one thing, you have to make assumptions about other things. And you don't really know if those assumptions are correct. So if it should be confirmed with laboratory experiments that there are sterile neutrinos, that would tell us, in turn, something very interesting about the cosmology that goes into deriving this constraint. People have made global fits to the data, assuming a 3 plus 1 or 3 plus 2 or 3 plus 3 spectrum. The bottom line from a relatively recent and very ambitious analysis is, first of all, 3 plus 1 spectra don't provide a good fit to the data. Assuming 3 plus 1, the appearance and the disappearance data call for very different values of the one big delta m squared, and the neutrino and the antineutrino data also call for different values of this delta m squared. Well, in the 3 plus 1 spectrum, there can't be any CP violation, so if you want to ease this neutrino-antineutrino tension, you can go to a 3 plus 2 spectrum, which can violate CP, and indeed, the nu versus nu bar tension is somewhat reduced, but the appearance and the disappearance data still call for very different mass splittings. That means that maybe there's yet another delta m squared in the spectrum, so you can go to a 3 plus 3 spectrum, and that eases the tension a little more, but there is still tension between appearance on the one hand and disappearance on the other. The appearance data, like Ellis and D, call for a relatively small delta m squared. The negative disappearance data call for a big delta m squared. Now, part of the reason that Ellis and D wants a little delta m squared is that rise at the very low energies. So some people are suspecting that that low energy excess should not be considered to be oscillation, but probably has some other source and should not be taken into account in the global fit. Then you would get rid of a lot of this tension. But that's the situation with the global fits.
You mean the low energy excess in Minibeam?
Yes, the low energy excess in Minibeam. Did I say something else? No, I'm sorry. Thank you for the correction.
If you take away the low energy excess.
Yes, if you put aside the low energy excess in Minibeam, then things are easy. Right. It's the low energy excess in Minibeam that is an outlier. And maybe just a plain liar. Okay, so are there sterile neutrinos? Well, obviously, whether you take the hints individually or you take them together, the case is not convincing. On the other hand, many people, certainly including me, think that the case is interesting enough to call for further experimentation, which hopefully will settle the issue definitively one way or another. Just about exactly a year ago, Fermilab created a so-called short baseline neutrino focus group, and in June of this year, that group came to the same conclusion, recommending a Fermilab experiment to look for mu to E flavor change, either this way or that way, with an ability to either rule in or rule out the existence of sterile neutrinos in the entire Ellis and D favored region. You are now sitting in the very, very dark, but I'm not, so I can continue, right? Looking throughout the world, there are a lot of very interesting ideas for future experiments that hopefully would be definitive on this issue of sterile neutrinos. I would like to just give you a flavor of the diversity and richness of these ideas by mentioning a few of them. The channels that you would like to study are E to mu flavor transition, both for neutrinos and antineutrinos, and the corresponding two disappearances. It's not necessary in principle to look for the CP conjugate of each of these processes, but of course, if you can study a process and its CP conjugate, you are testing things about your experiments, and you may even be testing CPT invariance. Now here I'm talking strictly about electron and muon flavors, It would, of course, be interesting to look for new tau appearance. It could be that the extra neutrino mass eigenstates, nu4, nu5, and however many there are, couple a lot to taus. We don't know that they don't. But I think experiments that can study new tau appearance are they're for some distant future time. So I'm going to talk about experiments that are in the electron and muon flavors. Both the charged current and neutral current event rates are interesting to study. In fact, one very appealing idea is to study the coherent scattering of a neutrino from a nucleus as a whole. In this reaction, the neutrino remains a neutrino, so it's a neutral current process. It would be mediated by a Z. Remember that the coupling of the Z is universal and diagonal. The Z doesn't care whether the incoming neutrino is a nu E, nu mu, or nu tau. So oscillation among these three flavors would not change the event rate for neutrinos to scatter coherently from a nucleus, but the Z boson does not couple to sterile neutrinos. So if an active neutrino, one of these three, oscillates into a sterile neutrino, the event rate for this coherent scattering from nuclei will oscillate along with it. And if you could see that wiggle of the neutral current event rate, you would be gaining evidence for the specifically sterile nature of what is going on, not just for a big delta M squared, but for the fact that an active neutrino is oscillating into a sterile neutrino. That would be extremely interesting. A word of warning, nobody has ever seen the coherent scattering of a neutrino from a nucleus. And here we're talking about using it for something. But why shouldn't we think big? So there are several ideas that have been proposed to do this. One of them would use electron neutrinos from an electron capture radioactive source. That's about 10 electron volts. So not only is the event rate small, but the recoil energy is very small, and both of those things make it very hard to detect that anything has happened. These are the same problems that you have when you're trying to detect dark matter. If dark matter scatters from a nucleus, first of all, the event rate is small, and second of all, the nuclear recoil energy is tiny. In fact, on an historical note, the barometric cryogenic detectors that some experiments are using to look for dark matter were originally thought of to look for coherent scattering of a neutrino from a nucleus. And then somebody realized, any detector that can do that has also got an application in looking for dark matter. And now this is coming full circle. People are using dark matter-inspired detectors to think about looking for coherent scattering of neutrino from a nucleus. Another idea is to use a cyclotron to make pions and then look at the decay neutrinos from the pi mu decay chain with the pions and the muons at rest. If you have two sources in different places in one detector, you can do your distance dependence and look for oscillation. The neutrinos from these decays at rest have an energy typically around 30 MeV instead of 1 MeV. So the recoil energy of the nucleus in the scattering will be 30 squared bigger than it was up here. So it's 10 kilovolts instead of 10 volts. That's still pretty small. And so people are thinking of using dark matter-inspired detectors. Warning, you're looking for a wiggle in the neutral current event rate. By having a big detector, having an array of detectors, or at least two detectors. If delta M squared is so big that the oscillation has already occurred before the neutrinos get to the closest of your detectors to the source, you're not going to see the wiggle. It already happened before the neutrinos reached your detector. That's neutral current scattering. Now let me turn to charged current scattering. You can again use a cyclotron to make pions, which make neutrinos, and you put this neutrino source right next to a really big detector. Again, as I mentioned, the energy of the neutrinos, let's say in nu bar decay from mu plus at rest, is typically around 30 MeV. With this energy and with a delta m squared around 1 electron volt squared, the first oscillation maximum in the oscillation is at around 40 meters from the source. So if the source is here and it's next to the proposed LENA detector in Europe, which is 100 meters long, you can see the wiggle as a function of where you are in the detector. That would be extremely interesting. And what you look for is nu bar goes to nu E bar, and then you detect the nu E bar in the detector by inverse beta decay. I mentioned that we would like to study nu E bar disappearance without using reactor nu E bars to see if the reactor nu E bars are truly disappearing. One idea to do that is to look for nu E bars from lithium-8 decay. You use a cyclotron basically to make neutrons, which then turn lithium-7 into lithium-8. The lithium-8 decays through nu E bar emission, and then you use a large detector to detect these nu E bars, again, by inverse beta decay. And if some of these nu E bars are disappearing, you're going to see a deficit of flux. And the claimed reach of such an approach, which is depicted by this heavy line, is really very impressive. This lost angle is sine squared 2 theta. Remember, an interesting level of disappearance in this mode is around somewhere in this region, and this heavy line goes well into that region. People have also proposed 2 detector short baseline experiments at accelerators, comparing event rates in a near and a far detector, which is a good way to deal with flux uncertainties so long as the neutrinos have not already oscillated before reaching the near detector, and you don't see any difference between the 2 rates in the 2 detectors. So it has been proposed to move the Icarus liquid argon detector from Gran Sasso to CERN and build a second liquid argon detector, and the claim sensitivity of that would exclude the entire LS&D favored region, which is here again in blue, or perhaps see something. And a similar thing is proposed for Fermilab. You use the microboom detector, which is under construction there, a liquid argon detector, as one detector, and you build a second liquid argon detector. And here is the sensitivity. Again, you could exclude at some confidence level the entire LS&D favored region. And finally, there is a very ambitious proposal called NuStorm, neutrinos from stored muons. It's a very low energy version of what is called usually a neutrino factory. You build a storage ring, you put muons into this storage ring. The straight section of the storage ring is pointed at a detector which can detect muons. And a typical energy of the storage would be around 4 GeV. And if, for example, you store mu pluses, they decay this way, and then you can look for the oscillation of nu E into nu mu, which you then detect through its production of a mu minus in your detector. Now remember that what LS&D reported was nu mu bar to nu E bar appearance. This reaction is the CPT mirror image of that. So assuming CPT, they have the same oscillation probability, and therefore this is the direct check of LS&D, and the claim sensitivity is very impressive indeed. You could exclude the whole LS&D favored region, which now is in orange, at 10 sigma, or perhaps discover something. If you would like to learn more about the hints for sterile neutrinos, there is a very thorough and very nice resource document, a white paper, which is given in this reference. In conclusion, if sterile neutrinos exist, that would obviously be very interesting because it means there's something quite different from anything that we've known up to that point. In addition, the sterile neutrinos presumably couple to something, not something in the standard model, but something. So that would motivate searches for that new physics at the LHC and elsewhere. So it would be very interesting to know whether those sterile neutrinos exist or not, but we want to know that definitively one way or another. Thank you.
Sorry to have interrupted you.
No, it's a pleasure.
But you also say that all these tensions are at the level of 1 or 2 sigmas. Also, as an experimentalist, I should not trust too much experiments in which the signal is claimed as something above a background that is calculated, is the compare with the data in a region where you don't expect the signal, and you extrapolate in the signal region, you find more than you foreseen and say that that is a signal.
Sure.
This is the way that SLND in both versions did, and the way that geometrically, and the way that Minibeam does. So if you don't know enough of the cross-sections, and you don't know enough the cross-section at low energies of neutrinos, then, I mean, you don't know your background.
No, that's right.
So you cannot claim such an important thing is on the basis of the background model. Now, I can hear the data, look back to the it is not calibration for the 2 neutrino detectors in Russia and in Gran Sasso. Sources have been used, a chromium source that was not a calibration source. It was Kirsten always refused to call calibration this procedure, as you said already, but was a way to test the detector, in particular to test the cross sections that were not enough known. And the Galax, for example, find 1 plus or minus 0.1 in the first calibration, and 0.8 plus or minus 0.1 in the second one. So it's one. If you average it, 1 sigma, more or less. But they never corrected the data multiplying or dividing by this number, because it was not for them a calibration, was just the text of the detector. So to trust the thing as done by Giunti and Laveder is something more than the experimentalists themselves have thought. So that, just let me finish that. To me, if you have 2 sigma here, 1 sigma there, and 3 sigma there, does not make 6 sigmas.
Well, I think if you're just asking about the statistics, in some cases, they have statistics that are much more than 1 or 2 sigma. But the question is, as you say, do we really understand the backgrounds correctly? Do we know the cross-sections correctly? There are a whole bunch of issues like that. And yes, I'm not an experimentalist, but I certainly feel uneasy about this. Also, nevertheless, it's not uninteresting, I think, that you have a hint, however unreliable it may be, from accelerator experiments, from a reactor experiment, from cosmology. To just forget about this, I think, would not be appropriate. But to accept it as something that's very likely is also inappropriate. I certainly agree with that.
To be complete, in the plot that you have seen, shown, with the limit of Bouguer, there is a symmetrical limit, but at lower, much lower mixing angles by Icarus. Carlo showed that in the public.
By Icarus, this is a limit on what specifically?
On neutrino muons going into neutrino electrons, electron neutrinos. That oscillation.
But mu to mu E is not the process that Ellis and D reported. Ellis and D reported mu bar to mu E bar, and they can differ.
When you spoke about CP violating effects, you were presumably referring to the P and NS phase or extension in the corresponding case when sterile neutrinos are included. Would you like to comment on the possible implications of additional phases of the neutrinos are of Majorana nature, at least 2 additional phases?
If the neutrinos are of
Majorana, the Majorana phases.
There is a general statement to the effect that you can't tell whether neutrinos are Majorana or Dirac by anything you can do in neutrino oscillation. Yes. So in particular, the Majorana or not Majorana nature of the neutrinos is not going to affect CP violation.
Yeah. So how can these phases show up? Would you like to comment on that?
Which, the Majorana phases? Sandro, are you going to talk about that? If you are, then I shouldn't answer this question at this point. All right. I'm tempted to begin the answer with a remark. They will show up with difficulty. But to be a little more specific, when you look for neutrinoless double beta decay, the rate for neutrinoless double beta decay depends on a number of things. First of all, it depends on the nuclear matrix element, which you don't know how to calculate very accurately.
Yeah.
Okay. There are uncertainties of factor of 2 or 3 in the matrix element, and in the square of that number in the rate. Secondly, they depend on the masses of the mass eigenstates and on various mixing angles, notably the solar mixing angle. Finally, the rate depends on the CP violating phases. Now, if everything else is under very good control, then you can extract from your measured rate the CP violating phase. This is not absolutely out of the question, but I wouldn't want to hold my breath waiting for it to happen, because there are so many other things in play.
So most of the phases continue to be elusive, Majorana phases by and large.
Well,
Hopefully, expectedly.
There was a group of people, including Andre de Gouveia and myself, who wondered once upon a time, some years ago, whether you could look for what you might call neutrino to anti-neutrino oscillation. This is a lepton number violating process, and that kind of oscillation, which is of course not what I was talking about, would be sensitive to these phases. The trouble is that the rate for neutrino to anti-neutrino oscillation is suppressed relative to the rate for normal neutrino interactions by a factor of the neutrino mass divided by the neutrino energy, all squared. Now you name your mass, divide by your energy, and you square, and I can describe succinctly your answer. It's small.
Suppose these sterile neutrinos existed. What good are they? And what I mean by that is, how do they couple in with other physics, such as dark matter? Could they be dark matter? How do they affect what you would see at the LHC, et cetera?
Well, first of all, there are a couple of people who entertain the possibility that extra neutrinos are, in fact, the dark matter. But they're talking about neutrinos that have masses like 10 to 20 kiloelectron volts, not the 1 electron voltish that we were talking about previously. But, you know, generically, yes, neutrinos could be the dark matter. Alex Kosenko at UCLA has been pursuing this for a long time. How the sterile neutrinos couple to other things of the sort that you could see at the LHC, I would hesitate to try to speculate on that. That is, of course, highly model dependent. But, for example, in left-right symmetric models, there is a right-handed, so-called right-handed W boson, which couples to right-hand V plus A currents instead of V minus A currents. And there are right-handed neutrinos which couple to that W boson, which are what we call sterile because they don't couple to the W boson of the standard model except through mixing effects. But then there has to be this right-handed W, and there have to be these neutrinos within the range accessible to the LHC. And there are by now some pretty stringent limits on such neutrinos coming from experiments other than, for example, B meson decays. I know you were looking for such things too.
So W decay
100% sterile.
100% sterile.
Okay.
So W decay won't give that sterile. Nu4 will not come from W decay.
Right. So that neutrino would not mix with Nu123.
So the UE4, U mu4, such terms will be identically 0.
What should be, say again?
This UE4,
yes. U, E, mu, and tau 4 are 0.
So in one of the expressions you had UE4 mod square, U mu4 mod square. this is the probability for nu mu going to nu e. So that expression will be 0 identically. So no oscillation.
No, that's right.
So
If you add a fourth neutrino and you make it 100% sterile, it doesn't mix, it doesn't play any role here.
So a sterile neutrino should also have couplings to the standard model particles.
Yes, of course.
In order to have oscillation.
Yes, of course. The thing that I was calling nu4, the extra neutrino, if you want it to be of any use to you, can't be 100% sterile. It has to have small couplings to the active flavors.
And the cosmology observables that you showed, presumably some of them do care whether they're sterile or active, or is that not the case?
When we had this focus group that I mentioned at Fermilab, we asked Scott Dodelson, who is a cosmologist, to please tell us what we're supposed to be believing and what we're not supposed to be believing, if I may describe it that way. And there are loopholes. If you don't take advantage of one of the loopholes, then the sterile neutrinos, as I mentioned, if they mix, not 100%, but mixing, if they mix with the active neutrinos to the degree that's required in order to explain the terrestrial anomalies in terms of sterile neutrinos, if you don't take advantage of one of these loopholes, they would have been present in the same number per unit volume as the active flavors. And to a large degree, the cosmological observables that I was talking about are affected by the presence of extra neutrinos through the effect of those extra neutrinos on the expansion rate, in other words, on the energy density. And that depends only on how much is there.
That is the BBN constraint.
Pardon?
That's the BBN constraint. Now, how about the large-scale structure? Does that?
The large-scale structure depends on the masses because so long as the neutrinos are relativistic, they are free-streaming and they suppress large-scale structure on, quote, small large scales. But when they are relativistic and when they are not relativistic depends on how much they weigh. And therefore, their effect on large-scale structure is mass-dependent. It's not, I mean, this is a mass effect. It's not sterile or not sterile. It's
but they have to couple, right, in order to...
no, I think it's just their effect on their effect on gravity.
All right, thank you.
It's also true that the electron-flavored neutrinos and antineutrinos have an effect on Big Bang nucleosynthesis. That's flavor dependent. But I was talking mostly about other stuff. I can tell you about some of the I can sell you a loophole later.
Just one very short, quick question. You mentioned about the energy of the muon for new storm. So my impression was for new storm, this very low energy version, they can only go up to about 3.5. Can it really go to 4? That's almost going into the LENF proposed sort of energies. Is that?
They talk about 4.
Oh, okay. I see. Okay.
Alan Glass, who's the principal driver, he talks about 4.
That's very useful.
And other things have changed. The length of the storage ring that I described as 150 meters was once 90-ish meters. It's in flux.